And we're back, and I hadn't gotten very far. I think it's on this slide, right? Ah, look, all of my work has also not been saved, but that's okay. So let's have our first clicker question now that we can see. Two resistors are connected in series. Come on, computer. There we go. Come on. You can do it. I don't know what went wrong here, but it's a spadoinkle day, as the song goes. Okay, now it's open for you to answer. So the connected in series with the battery is shown. R1 is less than R2, so we could say that's like 10 ohms and 20 ohms, just to put numbers on them. Which of the two resistors has the greater current flowing through it? All right. Well, we had a plurality here. Denford, which would you have chosen? Put it right on the spot. Not sure? Okay, well, the key for things being in series, like these two things are right now, is that they have the same current through them. So, because these two are connected in series, as both said in the problem and shown in the picture, then they have to have the same current. So by definition that they're in series, they had to have the same current. Now give me a second to make the next question available. Okay, now, which has the greater voltage? So the last one was current, and we established they have the same current. If this is 10 ohms and this is 20 ohms, let's say the current is 1 amp, just to make life easy. Which has the bigger voltage across it? Okay, this time we had a much less balanced, which is better. 7 out of 8 said R2 does. And those 7 are correct because voltage is equal to current times resistance. If we have the same current through both of them, then the one with the bigger resistance is going to have the bigger voltage. Final question of these three. In the circuit shown, so now instead of showing just R1, R2, I actually have values for them, 9 ohms and 1 ohms. The 1 ohm resistance is the internal resistance of the battery. It can be considered to be in series with the battery and the 9 ohm load. What is the current flowing through the 9 ohm resistor? Okay. we have 0. Okay, I'll tell you that at least one person got the answer right. So cross those two out. And let's look at the mechanism. How do you find, everything else aside, you want to find the current. What's your equation that allows you to calculate current? It's named after a dude named Georg, which would be George in English, of course. Relationship between voltage and current and resistance. What is that? We've been talking about it for a couple of weeks. Well, it's something similar to that. It's not I over V, no, but it is I equals V over R. If you solve that for resistance, resistance is V over I. I is V over R. Ohm's law. So what we need to know is the voltage and the resistance. Now it asked me for the current through the 9 ohm resistor. How does the current through the 9 ohm resistor relate to the current through the 1 ohm resistor? It has to be the same. What about the current through the battery? It's the same, right? They all have the same current because they're in series. So since they all have the same current, I can combine these two resistors into one equivalent resistance. What would that equivalent resistance be? 10 ohms. And so I could rewrite this circuit as 10 ohms and 3 volts. Why would I want to do that? Because now I know what's the voltage across my 10 ohm resistor. Three, right. 3 up, go through the 10 ohm resistor, it must have been 3 down. And so now I can put in the current for my battery is 3 volts divided by 10 ohms. And what's that? Three divided by 10. No one needs a calculator for that. Equals 0.3 volts, or 3 amps. And so the correct answer was our lone person with 0.30 amps. Now we had 4 people that said 0.33 amps. What mistake did those people make? It's very easy to make a mistake. What'd you say? Yeah, they said that the 3 volts was just over the 9 ohms instead of over all of it. Right? You have to be careful what your voltage difference is across. And so this 3 volts was across the entire circuit, not just across one of the 2 resistors. Okay, now let's move to, oh goodness. It is now not responding to my hand. It didn't crash, it's just it doesn't respond to my hand anymore. It's a bad day for electronics. So parallel circuit is a circuit when you put things in parallel so the tops and bottoms are connected. So now if I am going to track charge going through my circuit, I have current that, oops, I've still on the eraser, current that comes like this. So that's my total current. And then that current can go this way, or it can go this way, or it can go this way. So my current can be split up on any of the three paths here. So what do you suppose is the relationship between I total and I1? Start with the simple. In series, they were the same. What about here? They're not going to be the same. It's not necessarily going to be 1/3, but what I am going to have is the current that comes into point A, which is just I total, has to equal the current that leaves node A. We call it a node. What leaves there? I1, I2, and I3. So if I1, I2, and I3 are equal, then what you said would be correct. Now what about voltages? If I look at the voltage across resistor 1, relate to the voltage across resistor 2, relate to the voltage across resistor 3, how are those going to compare? They need to be equal. We did go over this in lab. They're going to be equal because the voltage is the difference between the top and the bottom. Well, the difference between the top and the bottom of these is exactly the same for all of them because the bottoms are all connected together and the tops are all connected together. And that's what it means for things to be in parallel. Now, when they're in parallel, because the currents add up and the voltages are the same, we can do just a little bit of mathematical manipulation. And we find that the total resistance, if they're in parallel, follows this equation. 1 over the total resistance is 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. Now, as an outcome, our parallel is always less than each of R1, R2, and R3. It's smaller than the smallest one. And when you think about that, it sometimes seems odd, like, okay, so I have things that it's hard to make charge go through. Remember, resistance is a measurement that's telling us how hard it is to make charge go through, how much energy we have to expend to make charge go through. And if I have two resistors, you think, well, that should be more energy. But if you think about the water analogy, as shown in this picture, it's like you have 3 different ways that the energy can go. And so even though you have 3 different ways, it doesn't have to go one, then the next, then the next. It does one or the next or the next. If one of them was very little resistance and one was very high, we talked about this, it'll just predominantly go through the little resistance because it's easy. It takes the easy route. And so if you put things in parallel, it's always going to make it less resistance overall because it's easier to get through because you have more possible ways of getting through. Now, I think I have a clicker question, but I want to do my... No, I don't yet. Okay. So here is the comparison between resistances in series and parallel when they are... Hey, it's back to touch sensitive. When they're in series, then the total resistance is bigger. It's the sum of each individual resistance. When they're in parallel, it's smaller because the inverse of the total resistance is the sum of the inverses. If they're in series, they have the same current. And if they're in parallel, they have the same voltage. Now let's go back to my demonstration here. And instead of having these connected in series, I'm going to change it to parallel. And of course, I do disconnect the power first because safety is important. So parallel, I have a red and a black on this, and so the colors don't mean anything. But I'm going to make all the blacks connected together. So I will connect all the blacks with blue. Black and blue, much like Rachel's chin. Okay, and then the other side I will connect. So put a red one to red. And, well, this one will have to do, it's longer. So now I have these connected all in parallel. Now, I have them out of order. I'll leave them out of order. This is the 100 watt, this is the 60, this is the 40. Connect the power, put the black to black, and the red to red. Once you get the color, actually doesn't matter. And plug it in, and which one's going to be the brightest? Which one? Well, I want you to think an answer, even if you're wrong. I don't care if you're wrong. I want you to think an answer. I want the thinking.
Whichever one that was the brightest before.
It was what?
I said whichever one was the brightest before.
Okay, whichever one was the brightest before. The one that was brightest before was the lowest watt bulb, so it was this one. In terms of brightness before, this one was brightest, then this one was the dimmest. Okay, thank you for answering.
Oh, geez.
Hmm.
Is the third one not screwed in yet?
Yes, the third one was not screwed in yet. I was like, there's something wrong. Okay, which one's the brightest?
They're all about the 100 watt. I say the middle one.
Yeah. The middle one is the brightest. They're all a lot brighter than they were before, aren't they? Every single one of them is brighter than it was before. The middle one's the brightest, then the one on the left, then the one on the right. It's exactly the opposite order of which one's the brightest. And we already saw what happens if I unscrew one.
Doesn't matter.
That one goes out, and it does not matter for the others. The others don't get brighter or dimmer when I unscrew it. They stay the same. That's my Don Knotts voice. Why do they stay the same? Well, let's just consider the circuit here. What I have right here is, that's my power supply. I use a little tilde because it's AC. And this is 100 watts, 60 watts, and 40 watts. If I disconnect this one, did I change the tops and bottoms of the others? No, they stay exactly the same. Now in terms of current, the current coming out of here was split three ways. If I cut this off, it took one of those currents away, so I had less current total. But each individual battery light bulb had the same. Now the way I drew this, you might wonder, what if he takes out the middle one? Does that change anything? Yeah. The answer is no, because if I take out the middle one, I'm really cutting it here and here so that it's still connected across there. So in parallel, when one goes out, the others stay unchanged. Now let's think about our household wiring. In your household, if you turn off a light, what happens to the other lights in the house? They should stay on and stay the same brightness. If they don't stay the same brightness, you have some wiring issues in your house, right? Because, I mean, it is possible, that you have some bad wiring and that can make a difference. But it shouldn't. In our house, you can turn off a light, turn on a light, you can plug something into the wall, unplug something from the wall, and other things shouldn't be affected. When they are affected, it's power issues, right, which is a bigger problem overall. So which way are our houses then wired? Are they wired in series or in parallel? They're wired in parallel. Why do you think that is? Yeah, so all the lights don't go out when you turn one out. It would be really inconvenient if they were wired in series. Now let's relate the power to what was going on here. What we see, I plug this or screw this back in, is that the 100 watt is the brightest here. Then the 60 watt, then the 40 watt, if they're in parallel. If you look at the light bulbs, you'll see that on the top it says 100 watts at 120 volts. So it's 100 watts if you have 120 volts across it. Like this, I have 120 volts across it. When I had them in series, the voltages were all smaller than 120. And the one that had the biggest resistance had the biggest voltage. So how do all these relate? See that little dot? That says my finger's there. As you can see, not there. How these relate is power is current times voltage. Remember, voltage is the energy per charge. Current, so I'm going to write these down just so we can see the relation. Voltage is equal to energy per charge. Current is charge per time, and power is energy per time. Energy per time. So it's pretty clear if I take the energy per charge and multiply it by the charge per time, that tells me how much energy per time. So power is always in electric circuits current times voltage. Well, if I have a resistor, I can replace I with V over R. Now this only works if it's a resistor. Doesn't work if it's something else like a power supply that doesn't have resistance. So power is V squared over R. This allows me to calculate what the resistance is for each filament, for each light bulb. Because solving this for resistance is V squared over the power for a light bulb. So 120 volts squared, 120 is 12 squared, you probably know, is 144. So if I have the 100 watt bulb, I'm going to take 14,400 and divide it by 100, and I will have 144 ohms. Now if I look at the 40 watt bulb, I'm only going to look at two here. Well, 14 divided by 4 is 3. 24 divided by 4 is 6. 6 times 4 is 24. So 360 ohms. I think I did that right. So you see that that 40 watt bulb had a bigger resistance. When I put them in series, because it had a bigger resistance, it had a bigger voltage drop across it. And because of that bigger voltage drop, it ended up actually having a higher power. We can take this equation here and solve it once more by substituting, instead of for VI is V over R, V is equal to IR, and we have power is equal to I squared R. So when things are in series and they have the same current, the one with the highest resistance is going to have the highest power. But when things are in parallel and they have the same voltage, then the one with the lowest resistance has the highest power. And so that's why the order of brightness was reversed when I did series versus parallel. Whoops.
Well, putting things in parallel always have that result?
Be specific with what result. So I think the answer is going to be yes, but I want to make sure I answer the correct question.
I mean, like, the opposite of putting them in series.
When you put them in series, the powers will flip, so the highest power is the lowest power. Always, yes. If it's just a resistive device. Okay, question here. Two 10 ohm light bulbs are connected in parallel to one another, and this combination is connected to a 6 volt battery. What is the total current flowing out of the battery? Actually, no, that is correct. Yeah.
I was going to say, if you're going to say it was wrong again.
Actually. That was bad of me. I should have thought it through. It was marked here as correct, but Zachary. Alrighty. 2, 4, 1, 0, 1. Now, because these are in parallel, there are actually two ways I can do this. Here's the first way, which probably to you is the simplest. Let's calculate the current going through each one. So if I count the current through, or calculate the current through each one, what's the voltage across each resistor? It's going to be all of it, because that 6 volts is going from the top to the bottom of each resistor. So I is V over R. For each resistor, that's 6 volts divided by 10 ohms. They're identical, which is 0.6 amps. So if I have 0.6 amps through each one of these, what's the total current I need? 2 times 0.6, which is 1.2 amps. Oh, I didn't see that you changed it.
I had it right the first time.
Yes.
Give me a look.
You had it right the first time. Okay, second way of doing it. Second way of doing it is saying, well, 1 over R parallel is equal to 1 over R1 plus 1 over R2. Now this is probably a little bit harder. 1 over 10 ohms plus 1 over 10 ohms. What's 1/10 plus 1/10? That's 2 over 10, or 1 over 5. So I have 1 over RP is equal to 1 over 5 ohms. Clearly, my R parallel is equal to 5 ohms. The total resistance for the two in parallel is half of what we started with. And then I is equal to V over R is equal to 6 volts over 5 ohms equals 1.2 amps. So two different ways of calculating the same thing there. In this circuit, are there any resistors that are in series? Got a yes? The correct answer is no. Because if things are in series, you have to have no other option but to go out of one into the other. If I have current that goes like this, it has the option of going like that. So R1 is not in series with R3. R2 is not in series with R3. And of course, R1 and R2 are not in series. Are any of them in parallel? Yes. And this time you're correct. These have the tops together and the bottoms together, so those two are in parallel. And then that combination is in series with R3. Okay. Household power was our last piece. I'm just going to skip 2 slides to get to... We use alternating current in our houses. That is, the power here is alternating, which means sometimes current goes left, sometimes it goes right. And so we draw, here's what it looks like. You have a sine wave, something that's a nice uniform. It's called a sine wave. That's a mathematical function. And it turns out the peak voltage, now this shows current, but the voltage peak is equal to the square root of 2 times the voltage RMS. RMS is you square the voltage, then you find the average, and then you take the square root. So it stands for root mean squared. It's not the same as average, because what's the average of this red squiggle? 0, because it spends as much time above 0 as below 0, and it's symmetrical. So VRMS is not the average, because the average voltage is just 0, and it's a useless number. You know, like, the average voltage is 0, and yet I electrocuted him. Because you had high positive and then high negative. So we use this RMS, and you take that RMS value, which is what we report. So when I say this is 120 volts, it's an RMS value of 120 volts. Multiply by the square root 2, and you get essentially square root 2 times 120 volts is about 170 volts. So the peak voltage coming out of here is 170 volts. But it goes from plus 170 down to minus 170. Okay, we're out of time, so out of time. Have a sweet day.